So this is a little video to summarize what we know about radioactive decay, meet the last kind of the law and sort of ideas, and do a bit of stuff to do with radioactivity. So let's start with our sort of key sort of definitions. When we have radioactive decay, one of the key sort of principles is that if we have an unstable nuclei, so we've got an unstable nucleus, it's going to emit, an alpha particle at some point. Okay, we have no ability to say for a single event when that will happen. So if we have one nuclei, we don't know when it will happen, and there's nothing we can really do to affect it. We can heat it up, cool it down. We can't really do anything here because the forces involved are the strong force. Within the nucleus itself, we don't really have much from it. So looking at one nuclei, utterly useless. But if we look at lots of them, so we've got a mole of them or whatever, suddenly we are able to deal with the law of large numbers. So that as radioactive decay is spontaneous and random, it follows that the more nuclei that are present in a sample, the more will decay in a given unit of time. Now this kind of idea that we're going to get more decays if we have more nuclei makes sense, because if we have a probability in, say, per second that 1% of nuclei were decaying, the more nuclei I draw, well, that 1% becomes a bigger number and we're going to get more decays. This idea, however, is at the heart of anything that is an exponential decay. That the rate of change is, so the rate of change, is proportional to the number that you've got. Okay, and this is kind of this is common. Okay, this is why as we've seen with coronavirus, exponential growth is very dangerous, because actually what happens is that as you get more infections, you get an ever-increasing rate at which the infections grow. And the same thing is happening, but in the opposite way with radioactive decay. The more nuclei there are, well, the more you're going to get rate of change. And the rate of change is what we call the activity. So mathematically, how this is written is the dn dt. So this is the rate of change. For those of you who love mathematics, yes, a differential. You can think of it as being of change in number over change in time. So the number you lose per unit time is proportional to minus, because it's going to go down. We've got a decay, not a growth. Is proportional to the number that we have. Okay, and that's sort of mathematically how it's formalized. Now, obviously, we can turn this into a lovely sort of equation by saying that actually can get as an equation. This can give us that dn dt is equal to minus a constant times by n, and that is where the decay constant comes in. Okay. Now the other way to write this, instead of writing it like this mathematical form, we can leave it as saying that this, therefore, the activity, or what we're going to call it A, is equal to minus lambda n. Now this is the kind of key thing. Actually, I don't really. I'm going to just write that as a symbol. So A is equal to minus lambda. Now, depending on where you go looking for your things, you'll most likely see it as this. A is minus lambda n. You might see it written like this, or written with triangles. But it's just activity is the rate of change. So how many have you lost per unit of time? Per second? Well, then your activity is going to be measured in the becquerel. So this is kind of what we get. Now, I'm going to do a little bit of a weird maths interlude. I'm going to just write something. This is sort of like, I'm going to go off and I'm going to do some quick integration here to show you. This is because this is our starting thing. This is what leads to our concept of exponential decay. Because what you have is you've got dn dt is equal to minus lambda n. You can then deal with this. It's called separation of variables, which you can therefore get 1 over n is equal to minus lambda, 1 over n dn minus lambda dt. Integrate both sides. And what you get is therefore that the integral of 1 over n is ln, so you get ln of n is equal to minus lambda t plus a constant. And we can integrate that. So then we can go, okay, so n is equal to e to the minus lambda t plus a constant, or precisely that e to this constant. Well, this constant is going to be where we started to, because if we if we say that n is equal to n0 when t is equal to 0, so if we set t is equal to, so what that would give us is n at a certain time is equal to e to some constant times by e to the minus lambda t. If we set t is equal to 0, well then this bit becomes 1 because it's e to the 0, which is 1, and therefore by definition this thing must be the number when n is 0, and that's what gives us n at a certain time is equal to n0 e to the minus lambda t. There we go. Smiley face for those of you who like integration or like mathematics. Now the same thing, because activity is defined in exactly the same way, like it comes from the same thing. You actually end up with you can end up with the exact same problem, that the activity, the rate of change of activity is also proportional to the activity. You end up with exactly the same sort of logic and thing, where you'd have dA dt is equal to minus lambda. You end up with literally the same thing, same equation, same stuff, which is why you then also get these different equations. If you don't like integration, you can ignore that, because you've seen it mathematically, you've worked through the problem, you know it's an exponential decay, but that's where it actually comes from. This is the fundamental sort of idea. And this is what allows us to work out various things. So I'm going to quickly go through the rest of it. So mathematical, wrong one. So mathematically, we can solve for the activity or number of remaining nuclei using the equations. We can either use n at a certain time is equal to the original e to the minus lambda t, so we can use that, or we can use the activity at a certain time is equal to the original activity times e to the minus lambda t. And you've seen that, you've seen that in terms of this exponential decay. So both of these decay exponentially with time. And therefore we have is, let's just quickly define our terms. So, or the key thing is this constant, which is called the decay constant. So lambda is the decay constant. And gives the probability of decay per unit time. Right. So that's how we've got to this. Now, therefore, to find lambda samples with I'm going to put in here, short half-life. So find lambda with samples with short half-life. We can plot the natural logarithm of n or a, depends, against t, and that gives us much like our capacitors, gives us our wondrousness. There's time, there's ln, natural log. Now we'll draw a nice sort of straight line. So we've got gradient is equal to lambda, and our intercept is going to be ln n. So that is how we can measure that is what we can do to get an estimate of the decay constant. Yeah. So there we go. That's our first. Right. This is kind of what we were doing. Let's So the half-life is defined as the time taken for half the nuclei to decay. And that means that n is going to equal n0 over 2, or a is going to equal a0 over 2. No, Siri thinks I'm talking to him. So, either our number of nuclei remaining is going to halve, or our activity is going to halve from what it originally was. So what we can do is we can see how lambda is related to t½ by setting t equal to the half-life. So if we take that, we'll get so we get n0 over 2. So that's because that's what our n has gone to, that is equal to n0 e to the minus lambda t. We take the logarithm of both sides. Before we do that, we can remember that that's going to therefore say that we've got a half is equal to e to the minus lambda t. So we get, so log of a half is equal to minus lambda t. And I think this is where a couple people were less happy with me, is that there's a definition, the natural log of half of 0.5 is just equal to minus the natural log of 2. These two things are the same. So instead of writing it as log of a half and minus, it's just nicer and neater to get rid of this. Oh, I've got to put this a half here. Okay, so it's just nicer and neater to get rid of the minus sign, because that would mean that therefore we've got the natural log 2 is equal to lambda t half. Okay, natural log of 2 is about 0.693, I think. So what we get is, so what that means is that we can say that the half-life is equal to the natural log of 2 divided by the decay constant. And that's one of the other sort of equations that we have to sort of use. So, as this goes up, this will go down. So as the decay constant increases, the half-life decreases. Okay, which should make sense. This is probability of decay. If it becomes more likely that decay has happened, well, then it will hang around for less time. Interesting aside, and this is you don't need to know this, is that actually 1 over lambda is also in physics defined as, is it tau? I think it's tau. And this is called the mean lifetime. And that's actually what that is it's the average lifetime that a radioactive nuclei will exist for. So if you want an average time it will exist for before disappearing, it's actually 1 over lambda. It's quite cool that there's this thing there called the mean lifetime. But obviously it's an average, and again, with all these things, you don't need to know that, but it's quite a nice little sort of thing that's defined. So, right, let's sort of go back. So yeah, so this is either a good way of measuring the half-life. Okay, what you can either do is you can have a graph like this, get your gradient, get your decay constant, and then you use your decay constant to therefore work out the half-life. Or your other way of doing it is to measure the half-life directly from a graph. So we can also measure the half-life from the exponential decay curve. So that would be if we plot the actual number, see, we will get a graph that will look like that. And if we have, it's blue again, so if we have that one there, and that is essentially, that is n0, we halve it, we get out here, n02. And if we halve it again, we're down to about here, n0/4. And this time here, and this time here. And of course, as we can see, these are perfect. This is perfect. I've done a perfect exponential graph. So yeah, this is, you've just done a load of this, so I'm presuming, hopefully this is the thing, but that's the kind of stuff that we kind of got to. So this is kind of where we got to. Lots of stuff. Now, interestingly, depending on what you're dealing with, it depends on what it is that's easiest to do. Now, this method is something where you're having to make certain sort of corrections and things. If you're drawing it by hand, it's there's a lot less certainty about drawing stuff by hand than sort of drawing a straight line. So this method, which you did at sort of GCSE, is not the most common method. Doesn't mean it doesn't work, but it's not necessarily the most common. This method becomes easier to do because drawing a straight line is it's an easier calculation to make. And also, you don't necessarily have to have an entire decay. You don't have to go beyond one half-life to be able to get the straight line. So actually, if you're measuring something for, a little bit of time, but not quite to one whole half-life, well, that's fine. You can take that. Maybe you just want to measure to one half-life essentially, but you don't want to measure to multiple ones. That's fine. So you can do it that way, and then you would get your gradient, and use this relationship here. Now the thing can be is, what about things that last forever, like some uranium-238, I think. Well, those ones that last 4.5 billion years. Well, what do you do with those things? Well, what you do with those things, you actually go all the way back to here. And this is where you have to be rather clever with what you do. So the best way with these ones is to recognize that your decay constant is equal to your activity divided by the number of nuclei you've got. So what you have to do is you solve that by making a pure sample. Okay. And then you measure that. And if you do that, then if you've made something that's pure, what you know is the activity. Like by measuring the activity, how much of these you're losing. In something like uranium, you can stick uranium-238 in a lab, and you're not going to measure any noticeable difference in the activity. It's got a half-life of 4.5 billion years. You're not going to measure something, but we are able to make very pure samples of things. We can make things that are purely something like uranium, and the time at which things are decaying while you're getting it into the position to sort of measure it. Well, you can essentially take activity to be essentially a constant. So you can take a measurement and go, well, okay, that number is pretty much going to stay the same. This number is going to be essentially the mass of whatever it was you were building, and then lambda is therefore going to become one of those things. Now, I did once, because I forgot what I was doing, I did once try and sort of like estimate this in the lab, and I forgot that the problem for that is that there's an inherent problem using Geiger counters, and if you've got a Geiger counter and you've got a sort of radioactive sample and you're measuring it, there's lots of problems with this. The first is that obviously everything that you're going, radioactive goes in every single direction. So you'd have to sort of either encase it maybe in a 360-degree Geiger counter, maybe, or you have to account for the fact of, okay, how big is my window compared to the volume of the sphere that this is all going out in, which is okay. You can do a correction for that. But the second more fundamental problem with Geiger counters, in a weird way, is that with Geiger counters, when a Geiger counter is taking a measurement, it cannot take another one at the same time. So what it can't do is measure two decays simultaneously. Now they're fast. They'll measure things very, very, very short time intervals. But if you've got a highly radioactive substance, you can actually be missing these things quite a lot. And that is actually also a massive problem. You have to spend a lot of time calibrating these things in order to do this. So if you tried just by simply measuring the activity of one of our radioactive samples that we got in school, and you tried to do this, you'd end up with a completely ridiculous answer, because simply it wouldn't, you would need to know the actual sensitivity of your Geiger counter and lots of other things besides. So it's really only something you can do at a university level, but it is doable, and it's how you get things. Certainly, I'm not going to be able to get a pure, few micrograms of uranium. I'm not going to be in a position to do that. But universities are able to, and it's reasonably common. So that's a thing that that's how this is the method by which, if you want to measure the really long half-lives of things, you don't actually measure the half-life, you measure their decay constant. So you're really getting an idea of, I've got let's say I've got 5 moles of them, and I'm working out of how many of them am I losing per second, and that can get you to a real probability. But you need quite accurate equipment to do that thing. You need to calibrate it. Which I haven't got the ability to do with the one in school. So so that's kind of the basics of what we've got. So let's do a quick couple of little written examples. So do a few sort of examples. So let's say we've got a sample has 10 to the 18 atoms. Its half-life is 2.000 days. Calculate 1, the fraction remaining. After 5 days, and to the activity after 5 days. And I'm 5.000, just making sure that we're going to that level of significance. So, right. Okay, so to answer that one. So the first one is, annoyingly, if it was 4 days, easy, you just do number of half-lives and just keep dividing by 2. But for this one, we've got to do, so n is equal to n naught e to the minus lambda t is the equation we want to know. We don't know the decay constant yet, so we need to first do that. So therefore, lambda is equal to log of 2 over the half-life, so 2.000, so t half, so it equals 0.691 over 2.000. So 0.691 over 2, and we get 0.3455. 0.3455. Okay. We can then do, now we've measured this in days, so that's days to the minus 1. So n over n0 is equal to e to the minus lambda is 0.3455 times t, which is 5.000. And we want to do an exponential thing on my graph there. And I get 0.177. So 0.177 is that. So this is the fraction remaining. Then if I do the 2, I want the activity after 5 days. So what I could use here is, I'm going to go with A is equal to lambda n. And so what I've got there is my activity is equal to lambda, which is 0.3455. 0.3455, so times n, and what I've now got is I've got this many, I've got that fraction of originally 10 to the 18 atoms. So what I've got times 0.177 times 10 to the 18, so I can do that. Times 0.3455, and I've got 6.14 times 10 to the 16 counts per day. Now I might want that in terms of the net amounts per second. I might want it in becquerels, which is the counts per second. So I could convert that into seconds by dividing by 86,400, which is the number of seconds in a day. And I also, so if we convert to counts per second, which is measured in becquerels, we would do activity is equal to 6.14 times 10 to the 16 over 86,400, and that gives us 7.11 times 10 to the 11 becquerels. And there we go. So yeah, right, okay, so there we go. There's our sort of like first sort of bit. Let's do another example. Okay, so we've got an isotope of krypton, so 8736 krypton, has half-life of 78 minutes. Calculate the activity 10 micrograms of 8736 krypton. Okay, so what we need to use here is we're going to have to use Avogadro's number. So what we're saying is that so this top number, remember, to a good approximation, that's a mole. So 1 mole of krypton is equal to 87 grams. So therefore we have 10 times 10 to the minus 6 over 87. Okay, so 10 and 10 minus 6 over 87. So we've got about my calculus by the way is 114 times 10 to the minus 9 moles. Okay. Therefore, the number of particles is Avogadro's number, so Na times n, so little n, which would be, if we were considering being consistent with our previous work. So we've got Avogadro's number, that is 6.02 times 10 to the 23, and that is this number here. So times 6.02 is 23. We've got 6.92 times 10 to the 16. 0.92 times 10 to the 16. And therefore we can sit there and say, so activity is equal to lambda n. Lambda is equal to log of 2 over the half-life. Let's get this one working in seconds from the word go. So that is going to equal log of 2 over 78 times 60. Okay. So we'd have this times by this. So our activity is equal to log of 2 over 78 times 60 is 4680 times by 6.92 times 10 to the 16. So 2 over 4680 times 16, and I get 1.02 times 10 to the 13. And this should give you a kind of a sense of just how much we don't pick up from our from our actual thing. So yeah, let's do one more. I've got a third one, so let's just do example 3. Say we've got a sample contains nope, sorry, not contains, I wrote the wrong word, so has an activity of 9 times 10 to 12 becquerels and a half-life of 80 seconds. How long does it take for the activity to fall to 2.00 times 10 to 12 becquerels? So right, so we've got in this one, we're going to use this one. Activity is original activity e to the minus lambda t. We are after t in this case. Okay, so we've got is we want activities. We can't here is put that in. So we want 2.00 times 10 to the 12 is equal to 9.00 times 10 to the 12 times e to the minus lambda t. So divide that through. So essentially we've got 2 over 9. We get the natural log of that is equal to minus lambda t. And then we want to know our value of lambda. Lambda is equal to ln 2 over the half-life, which is 80. So got, should really say natural log of 2. 8.66 times 10 to the minus 3. So yeah, so we've got 2 over 9. So we've got minus 1.504 is equal to minus 8.66 times 10 to the minus 3 times time. So we just now do what's happy is our minuses are going to disappear. And we got over 0.66 minus 3, and we get 173.7. So we get t is equal to 174 seconds. And there we go. That's sort of how we do it. That's our final sort of example. So that curve takes you through, problem solving using these things, and just how we can solve them. Okay. That's a lot of notes, but we're done.